Hello everybody. So far we have been discussing how to model a star. So let me first remind you that we started with these assumptions and I'll just remind you, I will not go through them in detail. We said that the star is isolated, it's spherically symmetric, all stars that we are looking are of same composition. There is local thermodynamic equilibrium, etc. And from the isolation came the fact that the mass of the star is constant. If I give you a particular mass, that is what changes in between the stars and changes the properties of the stars. We defined a few things. U as the internal energy, per unit mass. Q as the nuclear energy generated per unit time, per unit mass of the star. And we had L, which is luminosity, from a mass element M when by luminosity I mean that the energy going outwards from this mass element. So energy per unit time, that's why I call it luminosity, energy per unit time going outwards. And remember, because of the mass of the stars, we said that sometimes we'll use mass as our spatial parameter. Instead of R, we will use sometimes mass. That is more meaningful because the radius of the star changes, mass of the star doesn't change. Okay, so this is what we had started with, and then we arrived at two equations, u dot plus p, 1 by rho, time derivative of 1 by rho, so I put the dot on top of it, was equals to q minus del L del m. If I write the corresponding equation in terms of R, then it is u dot plus p 1 by rho dot equals q minus 1 by 4 pi r square rho del L del R. This came from the energy conservation, and from the momentum conservation, which is essentially Newton's second law, came this equation. We defined a few quantities. We defined omega which is the gravitational potential energy, to be integral of 0 to m gm dm by r. The total internal energy of the star was internal energy per unit mass times dm. We defined the nuclear luminosity of the star, which was Q integrated over all mass. And remember that this is obvious that, so let's write that the luminosity of the star, this is the luminosity that we measure from outside. This is what we plot in HR diagram. This is del L del M dm. We arrived at the fact that the core pressure is greater than gm square by 8 pi radius of the star to the power 4, and in case of ideal gas in hydrostatic equilibrium, we found that this equals 0. This is what we call the virial theorem. Okay, so before we go further, let us ask the question that we know the surface temperature of a star, but is the internal temperature of the star greater than the surface temperature or not? Now, how to do that? What we will do instead is we'll try to find out the average temperature of the star instead of the surface temperature. Okay, so let's start with the expression for omega. The omega is minus integral of 0 to m gm dm by r. So this is, remember, is the gravitational potential energy of the star. Now, you see what I can do here. I can do a trick here. The trick is the following. I can say that I take g capital M square by r outside minus of that. What remains inside, this integration now becomes 0 to 1, and this m is just a number x which is dimensionless. R is also a number y which is dimensionless. So x is essentially m by capital M and y is r by capital R. Okay, so if I do this integral will give me just a number. So let's call that alpha. And this will depend on how the density changes. Alpha will depend on how the density changes with the radius. So in general, I can write this equals minus alpha gm square by r. So alpha is a number, but we know now how the gravitational potential energy will change if I increase the mass of the star by a factor of 2 or decrease the radius by a factor of 2. Alright. Now, if the star is in hydrostatic equilibrium, so this we know is equals to 0. That implies for a star in hydrostatic equilibrium, U is minus omega by 2, and that I can now write as alpha by 2 times gm square by r. Right? Now U, we also know, is integral of UDM, and that small u is nothing but 3k T by, so small u is 3 by 2 kb T by the mass of the gas elements, because I have to make internal energy per unit mass. So it is equals to this. So I have now this equals to that. So let me do a little bit of rearrangement of this two equals. So I keep in the right hand side 1 by m, so 1 m from here essentially, and this integral over T dm. This is from 0 to m. So in the left hand side what I get? I have alpha, I have gm by r, and I have 3, 3 will come in the denominator, so let's keep the 3 here, and I have mg by kb. If I look at this I can write as T dm integrated from 0 to m by dm integrated from 0 to m. So this is like a mass average temperature. So I call this T average. So I get an estimate of the mass average temperature from here, which is given by this expression. So alpha mg capital G by 3 kb capital M by R. So see, if the radius of the star increases, the temperature will decrease and vice versa. This is something that will be of use for us today, later. Just like to give you an idea, T bar, if you put in all the numbers, you will see that this comes out to be 4 into 10 to the 6 mass of the star in unit of solar mass, and radius of the star unit of solar radius, obviously to the power minus 1, because radius come in the denominator. So you see that for the sun, this temperature is 4 into 10 to the 6 Kelvin, whereas the surface temperature of the sun is 6000 Kelvin. This is the temperature that we measure. The effective temperature we call is related to the surface temperature. If you assume it to be a complete black body, it is the surface temperature. So this star we are talking about is sun is 6000 Kelvin, and this is much larger than that. If the average is much larger, that essentially means that the interior of the sun or any other star is very, very hot. And that's the other reason, with the fact that the pressure is also enormous, is responsible for the nuclear fusion. Now we try to look at the total energy of the star. Okay, total energy budget. So you may say that we have already gone through an energy equation, but that energy equation talked about the nuclear energies, the internal energies. It did not talk about what happens if the star expands or contracts. So that will give you some kinetic energy also, right? So let us first define different types of energies that we have. So we have the gravitational potential energy. This we have already done, but we just want to look at it again. We call it omega, and omega is minus 0 to m What if I ask you, what is the rate of change of the gravitational potential energy? Now, the rate of change can only happen if you look at the right hand side for that small r. Because even again, remember, whatever we do, we are following that mass element. So that mass is independent of time. So 1 by r, if I take a time derivative, I will get minus 1 by r squared, r dot. So this I can write as 0 to m gm by r square r dot dm. Let's talk about the internal energy. And these are all of the star. So it's the total internal energy again. So this we called capital U. So capital U, remember, is defined as 0 to m small u dm. So again, if we calculate u dot, it will only change because of the change in the internal energy per unit mass. Now, when I say kinetic energy of the star, our star is a spherically symmetric object. So the only way its kinetic energy can change, and we are not talking, it's in isolation. So we are not talking about the kinetic energy of the star as the entire star is moving around, because we are just sitting at the star and measuring the kinetic energy. The only way this kinetic energy can appear is because if the radius of the star increases or decreases, which means that it will be for the r dot square. R is the radius of that, where that mass element dm is. So the kinetic energy is half r dot square dm for the mass element dm, and for the total kinetic energy you have to integrate it over all mass, and this we will call capital K. And just like the others, you can calculate what is the rate of change of the total kinetic energy. And again, so you have to do ddt of r dot square, which will give me okay. So these are the different types of energies that we are talking about. We can also ask the question, total luminosity of the star. This is per unit time. So this is q dm. Okay. So these are the different energy budgets, or in the right hand side of omega dot u dot k dot l star, and L gives you the change in the energies, and somehow they has to be equal, so which they has to balance properly, and that balance is what we like to see now. Okay, to do that we'll start with the equation, with this equation. which is the result from the momentum conservation or Newton's second law. So I have r double dot equals minus gm by r square minus 4 pi r square del p del m. You see that if I multiply this equation by integral 0 to m r dot dm, then I will get k dot because I have r double dot there. So I do that. So I multiply this entire equation, both left and right hand side, by r dot dm and then integrate over 0 to m. Okay, so this is what I do. In the first term, as we have just identified, will be k dot. And then I have minus, so this is coming from the first line, integral of 0 to m gm by r square r dot dm minus integral of 0 to m 4 pi r square r dot del p del m dm. Gm by r square r dot dm is nothing but omega dot. So this is k dot k dot plus omega dot, because the thing inside the integral is omega dot. So I take it left hand side, I get plus equals minus 0 to m you will agree that 4 pi r square r dot, let's try to work it out here. So if I have ddt of 4/3 pi r cube, which is the volume inside the radius r, this will be 4 pi r square r dot. So this I can also write for the shorthand as v dot. So this is essentially v dot del p del m dm. Right? So this is an calculation aid, so I keep it in a cloud. Let's go a little further. K dot plus omega dot equals minus. Let's do integration by parts, or we can write the integration by parts in the following way. This derivative del is operating on m, so I can write this thing as del del m of p v dot dm. So this will be p. Now the other one will take the derivative with respect to m. So this. First integral can be readily done because the m will cancel out dm. So what I will get is p v dot evaluated once at 0 and then p v dot evaluated at m. And then plus I have this integral. Let's have another calculation aid here. we know, let's write it here. So we know that rho dV is dm. So if I do dV dt, which is essentially what I have there, v dot, that is 1 by rho dot dm. So del v dot del m is nothing but 1 by rho dot. Here you see P, where the mass is m, which is at the surface. We argued last time, P at the surface is 0. So this is 0. What about V dot at the volume? Now the volume at the mass equals to 0, which corresponds to radius equals to 0, is always 0. If you don't increase the radius from 0, then volume never increases, whatever time you may wait for. So this is also 0. So you come to the fact that k dot plus omega dot is 0 to m integrated p 1 by rho dot dm. Here we see in this equation I have p 1 by rho dot. So if I integrate this equation over m, then I will get a term which I have in the other equation. So let's see what is this equation. U dot plus p 1 by rho dot equals q minus del L del m. So I have U dot plus p 1 by rho dot equals q minus what all I want to do is to integrate it over 0 to m. And you see readily this term comes out. So let's write that term equals to all the other terms. So that term is 0 to m dm p 1 by rho dot. This equals minus of 0 to m u dot dm. You see where we are going. And then plus integral of 0 to m q dm and minus integral of 0 to m del L del m dm. The left hand side is k dot plus omega dot. Right hand side, this you identify as capital U dot. See? This is here. And then I have L star as del L del m dm and L nuclear as q dm. So this is minus u dot. I bring it in the left hand side. So this is u dot. And then this is L nuclear. Minus L. This is the energy balance equation for the star. You see what is happening in the left hand side here. I have the kinetic energy, change in the kinetic energy. change in gravitational energy, change in internal energy, and in the right hand side is the net energy produced. Net because something is produced and L star is the energy which is lost from the surface of the star. So remaining is the net energy produced. So this is a very nice energy balance equation. And we can get all the equilibrium that we got earlier. So if we talk about thermal equilibrium, okay, by the way, so this also I can write as E dot where E is the total energy. In thermal equilibrium, I have L nuclear equals L star. So E dot is 0. Which means K plus omega plus U equals constant. So in thermal equilibrium, you see the addition of these three is constant doesn't mean that the kinetic energy will be constant. So the thermal equilibrium, the star can have kinetic energies that the shell, mass cell can go up and down if it wish, keeping the thermal equilibrium. If I have hydrostatic equilibrium though, in hydrostatic equilibrium, K is 0. And then R dot is 0. So if I have hydrostatic equilibrium, K is 0, then I go back thermal and hydrostatic equilibrium together. I go back to omega equals to U. And you see in this particular case, the total energy of the star, K is 0, it is omega plus U. Omega is minus 2U. Which implies E is minus of U. Internal energy is always positive. So this is less than 0. The star have negative energy. Also, temperature of the star, because E is minus U, that governs the energy of that star. Because of this relation, I can also write E as omega by 2. Okay, so now that we know about so much about the energy of the star, let us look at the dynamical stability and what we have learned about the energy, which energy increases for what change will be very much useful to understand the dynamical stability of the stars. And this understanding becomes a tool later, and we'll see how. Let's see what we know so far. Summarize here again. So I have the total energy, which is K plus omega plus u. The change in the total energy, time rate of change, is k dot plus omega dot plus u dot, and that is given by the nuclear energy produced minus L star. U, which is the internal energy, will depend on the average temperature. We estimated the dependencies on average temperature here. You see, it depends inversely on R. Remember, the mass of the star is fixed. That cannot change. The only thing it depends on here is there is a rough dependence on the density, because alpha comes on the how the density varies with radius. But the most of the dependence is coming from the radius of the star itself. So this goes as 1 by R. What about omega? Omega, you know, it goes as minus 1 by R. And just above. Now, this star may have come just out of the hydrostatic and thermal equilibrium, but if it is not much off, it is a little bit off from the hydrostatic or thermal equilibrium, then these things will be still roughly valid. So E will go as minus U. Okay, so these are the things that we will need for the next discussion. Let me remind you one more thing, which is that this is your knowledge from the nuclear physics, that L nuclear depends on two things, density and temperature, depends on rho and temperature. Okay, and so it depends on rho and temperature in positive manner. So let me call this to the power m and to the power n. So if rho increases, L increases, T increases, L increases, and vice versa. Okay, so let us keep this in mind. So this also means that depends on R to the power minus 3n and T to the power n. Now with this, before we proceed, let's make a dictionary. Let's ask the question, what happens if E increases? What do I see from here? Now E increase means, this implies this arrow towards the up means increase. Now U is minus E, so U will decrease. U decrease means T will increase. T will decrease. So T will decrease. U and T are proportional. But R is inversely proportional, so R will increase. And what about the internal energy? The internal energy, what about the gravitational energy? The gravitational energy will increase because it's minus of 1 by R. And there is one more thing, which is if T decreases, that will cause the L nuclear to increase. Okay, so let's use this. Let's say there was a star in thermal equilibrium. Suddenly, its nuclear output increases. How we are not asking right now. But let's say that somehow it sometimes what happens is if you are trying to balance your pencil on the tip of the pencil, if you move it a little bit away, it's very difficult to balance. You'll never be able to, because if you move it a little bit away from the equilibrium position, it will fall, right? So whether the star is in such a very complicated unstable equilibrium position, that is what we are asking. So say that the star is in thermal equilibrium position, but if I move it a little bit out of thermal equilibrium, then what happens? So this basically means that now my L nuclear has become greater than L star. That will imply E dot greater than 0. That will imply an increase in E. If E increases, then you have just seen in my dictionary that U decreases. Decrease of U means the temperature will also decrease. And decrease of temperature means decrease of L nuclear. Which will eventually decrease E, not E dot. So it will make the star go back to its original position. So increase the nuclear reaction a little bit. What that amounts to is the decrease of, it's amazing, right? So if I increase the nuclear reaction a little bit, it does not increase the internal energy of the star, it rather decreases the internal energy of the star. As the internal energy decreases, which means temperature decreases, the nuclear reaction rate also decreases. So the star comes back to an equilibrium. You can try the other way around, where you say that if I decrease the nuclear reaction a little bit, you can see then E will decrease, which means that now your U will increase, the temperature will increase, and it will increase the nuclear reaction rate. So this is built into the stellar astrophysics. This has a name, it's called a safety valve mechanism. So if a star, somehow the nuclear reaction rate increases, it does not go out of equilibrium. It comes back to the equilibrium. It may oscillate a little bit. Okay, now this is seen more dramatically in a certain type of stars. So let me draw a cartoon of the HR diagram here, and so remember that I have log 10 of T by T sun over here going this way, and I have log 10 of L by L luminosity here. Last time we said that we can also classify the stars in terms of their spectral classes. And there are these spectral classes O, B, A, F, G, K, M, etc. For example, Sun is a G-type star. Now, here I have the main sequence. And remember that there are stars which are out of the main sequence also. And we talked about last time a little bit that if you look at different clusters, we see the top of the main sequence keeps on decreasing, depleting as the age of the cluster increases. So some stars are found here, and these stars are seen. So there are different types of stars even here. This region in the HR diagram is called instability strip. Because in this region, the radius of the star oscillates a little bit. Well, I don't know why it is exactly called an instability strip, because the star doesn't become unstable. It still is a stable, but it's not, doesn't stay exactly with the same luminosity, because remember that the luminosity depends on the radius of the star. So let's see what happens for these stars. These stars have, so remember that the stars have both hydrogen and helium. Now, these stars, if I draw a cartoon of these stars, and I want to draw only the helium content for a certain reason. The outermost region, the helium is neutral. Then you get helium 2, and then you get helium 1. Sorry, helium 3. So there, so helium 3 is inside. So they are ionized states of helium, singly and doubly ionized. For helium 2, you need a temperature to ionize this. You need a temperature greater than 25,000 Kelvin, which is an enormous temperature. And you see that the solar temperature, surface temperature is 5,000 Kelvin. At the surface of a star, the temperature can be 10,000 Kelvin, but not 25,000 Kelvin. So the helium is not ionized at the surface, but once you go inside the star, the temperature increases. At some point, the helium is ionized. So the singly ionized is helium 2, and then I get helium 3, which has greater than this much of temperature. Okay. Now what happens for this star is the following. So you have a contraction. Contraction means that the radius decreases. What happens if radius decreases? Remember that the average temperature is inversely proportional to radius. This is not the surface temperature. What I write here as T effective is the surface temperature of the star, that is different than the average temperature. But if the radius decreases, the average temperature increases. Now, as the average temperature increases, an additional thing happens here. The temperature goes beyond 35,000 K, so He3 is formed. So He2 turns into He3. This makes the medium opaque. Okay. So as the medium becomes more opaque, obviously more photons will be trapped, and that will increase the temperature even more. So this increases the temperature even more. So there's more increase in temperature like a rocket. What will that give? It will increase L nuclear. That means E increases, total energy of the star increases. And now, if the total energy of the star increases, then U has to decrease and the radius has to increase. And that brings the star back to its original position. Now, this will keep on happening in such stars, which means the net result of this is an oscillation of the radius of the star, which in turn will give an oscillation of L star. Now see, we said that L nuclear increases, and it's also the fact that L star increases. So if you do the detailed calculation, you will see that L nuclear minus L star also increases. Because of that, the oscillation happens. Otherwise, you may think that because the L star increases, it may take out all the L nuclear, so E will not change. That is not the case. Okay, so what happens as a result of this cycle is that the star goes up and down in this strip. So its radius increases and the temperature decreases a little bit, and this keeps on happening. I'm sorry, the radius and the temperature both increases and both decreases, and this keeps on happening. So one of such stars, very famous, are called Cepheids variables. And the other, so which lies around that region, and then there are rather smaller variation happens for stars called RL Lyrae. I request you to look at these stars separately. The Cepheids, if you plot the apparent magnitude, and now this can be just the apparent magnitude because the absolute magnitude, the change in the apparent magnitude will be the same as the change in the absolute magnitude. So if I plot the change in the apparent magnitude in terms of days, and you see this is completely governed by the physics of the star. So what will be the time period of such oscillation? I can just calculate from the physics of the star, and it will depend on the mass of the star, the luminosity of the star, these type of things. Mostly mass of the star, because remember that is how we are parameterizing our star. So it looks like this. So about few days time period oscillation, and then it can change by even few magnitudes. The apparent magnitude can change by few magnitudes. So 4 is a dimmer star, 3 is a brighter star. Remember the magnitude scale, again the dimmer comes with larger value, the brighter comes with smaller value. Now what we can do is, from the physics of the star, we will know luminosity of the star as a function of mass and time period of oscillation also as a function of mass. So we'll know it in terms of the luminosity of the star. Okay. So reading the time period here, I can get, so from time period, I get the luminosity, which will give me the absolute magnitude, and we observe, so say this is the V band magnitude, MV. So this now I can use as a distance modulus. In fact, this is how Edwin Hubble measured the distance to the nearby galaxies and found that the universe must be expanding. We'll carry forward in our discussion about the stellar structure in the next lecture again. Thank you.